Good afternoon, everyone. I am Tony Robinson with MAP, and welcome to today's webinar titled Unveiling a New Era in Injection Molding, the Autonomous Breakthrough Case Study, presented by MAP partner RJG. Just a few notes before we get started. I will try to keep all attendees muted throughout the presentation, but please keep yourself muted as well to eliminate any background noise. We are recording the webinar, and it will be up on the webinar archives page in the next few days. If you will need a member login to access that page, so just reach out to us if you need any help with that. There is time for questions at the end of the presentation, so please use the chat feature to ask any questions that might come up throughout the presentation, and we will reach those later on. And if you have any logistical issues, you can also use the chat, and I will help you troubleshoot. So with that being said, Brandon, I will turn over to you.
Thanks, Tony. Hello, everyone. Brandon Birchmeier here with RJG. I'm a senior client solutions consultant with RJG. Just had my 1 year anniversary last month being part of the RJG team and infrastructure. And today I'm talking to you about autonomous molding and a lot of new efforts that RJG is putting into the autonomous molding technology, autonomous molding world. And I have some cool information to share today about breakthroughs in the autonomous world that you get through the use of cavity pressure sensors made by RJG. So lots to get through today. I'm going to start going. We have a lot to talk about. And we're going to start today's conversation really talking about the evolution of the injection molding process. First, how did we get to where we are? Which I think is important, especially for context as we talk about autonomous molding. Let's start way back, in the Wayback Machine, early years of injection molding, right? What was the process? What was the methodology? And that was all boost pressure, right? So you would use pressure in the machine, a high hydraulic boost pressure, and it was kind of a feel thing, right? You were just using pressure to fill the mold, and if you had sink marks, short shots, things like that, you'd use more pressure. If you had flash issues like that, you'd use less pressure. So it was just a hydraulic boost pressure was really controlling the machine. It was kind of really pressure focused, right? You just packing it in there. And then, in the 70s, up into the 90s, we started getting, we were starting to understand, the value of virology in injection molding and shifted to a velocity-driven filling strategy, right? Which helped with faster cycles, better efficiency, able to handle more viscosity shifts, for example, because of the things we learned about virology. And then we created the switchover, right? We had to transfer from that velocity stage to a pressure stage. So you're first getting a little bit of that decoupled philosophy in this era. But again, the machines kind of did the same thing over and over, weren't really capable of handling variation. Then in the 90s, RGG played a big role in this up into the current, scientific molding principles and standardized process development. Why decoupled molding and is so impactful and successful in our world is it created a methodology and a foundational base of knowledge to grow, philosophy out of, the philosophy of how you develop an injection molding process. So it was a repeatable, systematic approach to developing an injection molding process. Again, we're using velocity to control the fill. You'll have a pressure-based pack and hold. But through decoupled free molding, right, we could use cavity pressure as a feedback to allow transfer to happen. So not full autonomous, but now at least the mold and the material in the mold had an influence on machine control, which takes us into the present in adaptive low constant pressure molding, or iMFLUX, as you may have heard it called as well, which is it's always pressure control. So this is pressure process where we're adapting the velocity in real time based on the input from the machine. And there's two really neat algorithms built into the low constant pressure molding process. One is auto viscosity adjust, and the other is process factor A. We'll dive into those more in this presentation, specifically about how they handle and adapt, provide an autonomous feature and closed loop in your process. And what's neat about this methodology too is it really has a broad processing window. If you're dealing with a lot of variation in your raw material, you want to run more recycle, more regrind, more post-consumer regrind, more industrial regrind. This system allows you to do that. It's really meant to embrace variation. In eras prior, we would probably avoid variation, right? Well, this low adaptive constant pressure process is thrives off variation. It's meant to handle that. So a little bit more background. Why am I talking about this? Well, this past spring, early summer, a big announcement. RGG was adding the iMFLUX technology to its portfolio. So a lot of the intellectual property that used to be housed under the P&G umbrella, RGG has obtained that. And that is my background. To be clear, I was part of technical director for iMFLUX for 10 years, helping to develop this technology. So that's why I get really excited about, as it continues to evolve and the paths we're going down. So the background of this, what is this? What's this case study about? This case study is about how do cavity pressure transducers impact a constant pressure process? So we already know they've revolutionized a molder's ability to mold from the plastics point of view, right? Through transfer, right? So today, your post-gate sensor, your end-to-fill sensor, you can utilize that to close the loop on transfer in your machine, right? So we're using the plastics point of view to dictate some level of control, right? And that was the first kind of iteration of the plastic influencing machine control through the transfer. But what we wanted to explore in this specific case study or set of case studies in white paper was how do cavity pressure sensors influence the two autonomous molding algorithms, one, process factor A, and then two, auto viscosity adjust. So the first thing I want to talk about is, it helps to get an overview. What is low constant pressure molding? For those of you who haven't gone through this, let's cover that real quickly so everyone comes up to speed kind of about the methodology and philosophy around constant pressure molding. So the way this system works is there is one output that comes out of the control box, the iMFLUX control system, and that is an inject signal. That's the voltage that's being sent to your screw that tells it how fast to go, essentially. More or less voltage dictates more or less screw speed. And that is done to maintain a constant pressure on a nozzle pressure sensor that is installed on the machine. In addition to that, cavity pressure sensors installed in the mold, like an RGG sensor, can use the information from this process to feed it back in. So again, we're bringing these inputs in, a nozzle pressure sensor, a cavity pressure sensor, and then other things like the machine hydraulic pressure, screw position, something called run input that tells us when we can take over control of the machine. Bringing all these inputs in, our single one output is again injection signal voltage to the screw to drive velocity to maintain a pressure. So let's talk about that again, that philosophy a little bit more. First, let's talk about the decoupled molding, right? The industry standard, like I'd mentioned before, you have a velocity controlled fill phase. As speeds maintain, your plastic pressure, which is this blue line here, increases until you achieve your transfer point, right? And then you are then holding pressure in time until you achieve gate seal. So you have independent decoupled phases, your fill phase, your pack phase, cooling phase. How iMFLUX is different is there aren't independent phases, really. It is all a single pressure control. And that's what this green line is representing. That is your constant pressure control in the iMFLUX process. And you'll notice you get this unique velocity relationship out of that. What we're looking for is a lot of upfront speed. Again, we want to take advantage of the rheological properties of that polymer, the shear thinning properties. So we still want to mold fast when we can. So we get a lot of upfront speed as pressure achieves set point. But once pressure set point is achieved, you'll notice this velocity decelerates. To maintain pressure now, I don't need all that speed. My speed naturally decelerates. And this deceleration allows the part to pack while it fills. It becomes a really efficient use of the screw, right? I'm doing two things at once, packing that part out while I continue to fill it. Allows you to do, things like family molds. You can handle a lot of viscosity variation. And one thing I want to point out is you have independent tuning capability. And this is important when you get an iMFLUX controller, you have independent PID control so that you can get the response you want out of your machine control. Usually those tuning levers are not available to your typical operator. Those are kind of buried in your machine control. In order to get the response we want, we do have independent tuning capability so that we can get this look. you go out to your machine today and try to run a constant pressure process, you may not get quite the response you're looking for in your tuning. Again, depending on your machine. So it's a much lower pressure process. It does take longer to fill. 95% fill was back here on your time scale in the decoupled process. Here it is much farther out. However, we're able to eliminate the additional pack and hold phase. So if you think about injection time forward, this is a shorter process. And some of the benefits you get is one is this packs as it fills, right? So I'll show you a few of these examples. We're going to revisit this part. This part is actually part of our case study. For those of you who have little kids, maybe you recognize this. It's a Pampers wipe lid. And this is, your traditional short shot. What does a short shot look like when you control with rheology-based injection speeds? Well, you're not densifying that material. You're really skinning that layer of plastic to the steel. So when you make a short shot, you don't have a densified part. You have lots of orange peel, sink marks, right? This is why we have a pack phase, because I need to fix all this, all these defects I kind of created during the fill phase. Well, you pack as you fill, right? So I get that high initial velocity and then the deceleration. I am densifying this part while I continue to fill it. Instead of having to come back and fix these defects that occur during my fill stage, I try not to let them exist in the first place, right? We're not allowing the plastic to ever relax. So today you fill at a constant speed, and when you transfer, you're going from a very high pressure to a much, much smaller pressure typically. And it allows the material to relax. And now you need to re-densify this through your pack phase. Again, a big part of the philosophy here of this influx process is not have to go back and fix those things. I'm going to densify this part while I fill it so that when it's full, it's done, it's ready, it doesn't have those aesthetic issues. Another, just kind of some overall, themes about low constant pressure molding. Another area of improvement is reduced stress, right? So when you reduce peak pressure, say 30 to 50%, which we do on average, you're getting a lot of less residual stress captured in your part, especially near your gate location. So these parts here are gated at the bottom here. And you capture a lot of stress. This is polycarbonate, on some polarized film. You can see the stress concentrations in that part required to fill this part and then again pack it out. Here's that same part with low constant pressure molding, and this part's going to want to warp less than you would traditionally, again, because you're not capturing all that stress in the part during your pack and hold phase, trying to achieve gate seal. Balance of fill. I mentioned family molds earlier. This kind of true of all molds. Balance is so important in our decoupled process philosophy because the pressure continues to increase in the system, right? If I'm maintaining my fill speed at a constant rate, that first cavity to fill is going to be my heaviest cavity. And the reason is that the pressure continues to increase in the system. So my first cavity is to see pressure. And what you're seeing here is a 16 cavity mold with a pressure sensor in each cavity. The first cavities to see pressure see the most pressure. Unsurprisingly, right? Because the pressure continues to increase in the system as I try to fill all my cavities out. So those first cavities to fill are always your heaviest cavities. There's a very strong correlation between short shot weight and finished part weight. The influx process, that's not really the case. Again, this is maintained plateaued pressure here. So I still have the imbalance. In fact, you can see it, right? Those last cavities to fill are actually, probably more imbalanced than they were in this first version. But the delta in the peaks of pressure are much, much similar. We're narrowing that distribution because as I try to pressurize these last cavities to fill, I'm not over pressurizing the first cavities to fill. Why? Because I'm maintaining pressure in the process. So I'm allowing these cavities that are filling last to catch up to those cavities that filled first. That's not really possible when you're controlling with velocity. Again, that you're not controlling the pressure. The pressure is an output of that process. So as that speed's maintained, that pressure continues to increase and you see the imbalance. Again, that's why balance is so critical to success in the conventional molding process. Okay, so we broke down, what is low constant pressure molding, what is influx molding. Now I kind of want to get at the specific algorithms and how cavity pressure sensors can really improve these. The first one is process factor A, for lack of a better name, process factor A. So before I talk about what process factor A is in the influx process, let's first talk about how cavity pressure sensors influence decoupled molding. And today you have a binary response with pressure. And what I mean by that is you are controlling transfer either from a post-gate sensor pressure
Bukan,
or an end of cavity sensor, right?
bukan.
So if I say I want to transfer at 500 psi of end of cavity pressure, once that I achieve 500 psi pressure here, the machine will transfer into my pack and hold phase, right? So you're closing the loop on transfer. But it is a binary response. We're using one part of this curve, one data point on the curve to make that determination, right? You're just saying, what is my target pressure that I want to transfer my machine at? And this is how decoupled 3 molding utilizes the cavity pressure sensor today, right? Which is, admittedly a huge improvement over a decoupled 2, where you're relying completely on screw stroke, right? The mold itself isn't really part of that equation. Decoupled 3 molding with the use of cavity pressure sensors to control transfer is really that first foray into, okay, my mold, it's the thing I'm molding is now playing a role in how my machine controls. And what's neat about that is I really think, constant pressure molding is taking this to another degree. And what I mean by that is it's a direct ratioed response. So the way process factor A works in an iMFLUX process is, again, I have a constant plastic pressure. As I see end of fill pressure in my cavity, what we have is it mirrors that response. So as my end of fill sensor pressure increases, my driving pressure is mirrored in the response. It mirrors how that cavity responds. Once I achieve my peak in that pressure, it'll plateau out. You can almost think about this as your hold pressure, right? It'll automatically figure out what it needs to plateau out at based on when the peak pressure is achieved in the end of fill. What I love about this is that all this topography is playing a role in your control, right? Before I talked about binary control, the genius of Rod Grollo and the cavity pressure sensor, I feel like is getting more exemplified because it isn't one point of pressure in time, right? So again, you decouple 3 molding, my pressure set point, I want 500 psi in my end of fill sensor. When it achieves that, it'll transfer. So you're getting a binary response out of that sensor. Through PFA, again, it's a direct ratioed response. This topography, this profile is playing a role in all of this response. So there's a really direct connection between the topography, the curvature of this cavity pressure, and the response of the machine, which I think is really unique and really like, how do you maximize the use of a cavity pressure sensor? I feel like this is a really good way of going about it. And this would be an example of a PFA -1. So it's a 1-to-1 ratio. So for every 1 PSI of cavity pressure sensor, I'm dropping my driving pressure by a -1 in the opposite direction. A -2, for example, would be a 2-to-1. I would drop this 2 PSI for every 1 PSI end of fill sensor. So that is a setting in the controller, PFA, that helps you determine what's my ratio of response to my cavity pressure. And again, I only really recommend this in end of fill. We'll talk about that some more later on in the presentation. So naturally, if I use a multitude of different PFAs, I get a different pressure response. And that's what this image is showing here. So same process, right? Constant pressure coming across. And then I have different PFAs, a PFA of -2, 1.5, 1, 0.75, -0.5, even a 0 and a positive 0.25. And you can see how that impacts the cavity pressure, right? When this one goes way up, that's that plus 2.25. It's kind of an additive effect. You can see on the -2 how much the pressure drops relative to the cavity pressure. So this scaling of this cavity pressure is a real-time input to how I get to a lower pressure, right? You can kind of almost think of this as our method of transfer as well, but it's very subtle and very smooth. Today your transfer, you transfer at that, even if it is decoupled 3, I got to get from a high fill pressure to my hold pressure. Well, things like screw can bounce back. There's a lot of noise in that part of the process, right? What we're trying to do is transition into a lower pressure, but do it as smooth as possible. And here you can see the screw movement. The screw is not bouncing. It is very, very smooth movements through here as we transition from one pressure to another. It is much less violent in your mold, and to what the part experiences as well. So, but as you can see here, cavity pressure does scale with the PFA changes. And here you can kind of see this. This is a bunch of overlays doing a pretty massive viscosity shift. So I think this is going from like a 7 melt to like a 50 melt example. So here is that driving pressure. This is auto viscosity adjust driving this process up and down, which we'll talk about next. But here you can see cavity pressure, and you can see the response to cavity pressure in this part. So this is a negative zero point 0.2. So it means for every 1 psi of end of fill pressure I'm seeing, I'm dropping my driving pressure by 0.2 psi. And that PFA is maintained from that high pressure down to that low pressure. Again, just a bunch of overlays of shots and what that would look like. So this is important. This is important because this is what happens when you utilize a cavity pressure sensor. But when you don't have a cavity pressure sensor, you have to create a virtual version of what I just showed you. So you have to go into the iMFLUX controller and you have to say, what do I want the shape of my curve to be? What pressure do I want to achieve? And that is all user defined. So a user is now defining, when a cavity pressure sensor is absent, it's defining what that shape should look like and what that response should look like. The other thing that happens is it doesn't change. Like it always assumes the same shape, which we know by looking at this that's not necessarily the case. As I change my PFA, I'm getting a different response because it's the real deal that's feeding back. When I'm using a virtual cavity curve, it doesn't scale. It always assumes the same shape in the curve. So you do lose some capability going to the virtual cavity curve setup, which we'll dive into in the case study. So that was process factor A, the first autonomous algorithm. The next one is auto viscosity adjust. So what is auto viscosity adjust? Auto viscosity adjust is us basically turning the barrel into a rheometer. For those of you who are familiar with how an MFI is determined for your resin, your melt flow index, you put a constant weight on there. The crucible is heated up and plastics extruded through that mechanism, and you collect it, and you see how much you collect over a certain amount of time. It's a constant pressure process. So what's neat about the iMFLUX process is when I'm molding with constant pressure, fill time is a true output of my process. Today, you may measure fill time, but you have a lot of control over it. You say, this is my shot size, this is my transfer, and I'm going to travel this fast. So you kind of dictated what your fill time should be with those settings. When you mold with pressure, fill time's 100% up to the geometry of the mold and the material you're running it at. So what I mean by that is once you set up kind of a good, stable process, you can turn on auto viscosity adjust. And what it's going to do is scale the driving pressure, either more or less, to achieve a target fill time. That target fill time can be achieved through something called melt travel, which I'll touch on, or through cavity pressure. So what we're doing is getting a real-time fill time feedback, taking that information and applying it to our driving pressure. Do I need more or do I need less pressure to achieve my fill time target? That's how auto viscosity adjust works. And here's another little example of that, going through a living hinge. Again, you get this unique injection speed profile through this hinge part, but it's getting a read on fill time. If my viscosity increases, I know I need more pressure. If my viscosity decreases, I need less pressure. So what the system is doing is, again, getting a read on how fast or slow the part fills, and then making an adjustment to auto viscosity adjust to utilize more or less pressure. This allows you to handle really massive changes in viscosity, for example. So, like I mentioned, auto viscosity adjust can be set up in one of two ways. You can either do it in melt travel mode or cavity pressure mode. So here is that iMFLUX controller, the modes that are available to you, cavity pressure and melt travel. Let's talk about melt travel first. So melt travel is a unique kind of iMFLUX constant pressure metric. So what it is the distance the screw moves once the desired pressure is achieved in the machine, right? So there's that nozzle sensor I had mentioned earlier. What we're going to do is we're going to create a target for in pressure to zero that screw out at. So as pressure increases, the screw starts to move forward. I'm going to say, let's say 2000 PSI. Once I achieve 2000 PSI, it's going to zero the screw from that point so that it's only looking at travel from when the melt has been compressed. All the travel before compression is ignored. It's only looking at travel once compression's occurred. The idea behind
Right,
that is, right,
right on the
with a
corner.
check ring and decompression, a lot of noise or variation can occur in that first movement of your screw. What we want to do is take advantage of having that nozzle sensor and saying, okay, I'm going to zero my screw from based on compression of the material, and then look at movement from that point forward, which gives you a much, I would say, accurate reading of screw travel relative to compressibility in your resin. So the what you're looking at is how much has this screw moved from that 0 point. We call that melt travel. And that is a way for us to say, what's my melt travel time target? Maybe I want to move 3 inches in 3 seconds, for example. That would be the target. It's going to say how far has my melt traveled versus my target, and it'll apply more or less pressure to that. So again, just like I mentioned, I may say, hey, I want this to be 3 inches. Maybe this is 3 seconds of time. That is my target. I want to achieve that travel target every shot. And that's what auto viscosity adjust will use to drive the pressure. Alternatively, and one I'm proposing today is using cavity pressure to provide that time target. So in a similar fashion, right, we have our plastic pressure. I have my end of fill sensor, my PFAs coming into play there. And then what I'm going to do is I get just similar to the melt pressure, similar to transfer as well. I'm just saying I want this much pressure in this amount of time. So in this example, maybe I want 500 PSI of end of fill cavity pressure in 3 seconds. So again, auto viscosity adjust will use more or less pressure to try to achieve that fill time target every single shot. That is how auto viscosity adjust is modifying the process for us. Okay, so that was a lot of buildup. I had to set the stage a little bit for the case study because the things I just explained, we wanted to experiment directly and understand the benefits of cavity pressure in these scenarios. So what was the case study? So my good friends, P&G, again, the folks who helped develop the iMFLUX technology, they collaborated with us and we chose 3 different molds and machine combinations to understand the impact of cavity pressure sensors to part quality. So one of the molds was a baby care wipe lid. You saw a picture of that earlier with the short shots and the angle. Small ASTM mold. This is a family tool, has some ASTM bars, a circle on it. That ran in an Arberg, and then a dose cup for any of those who like for medicine. A small 4 cavity dose cup that was running in a robo shop. And this is the experiment. So we ran DOE conditions. So we really big DOE. We had 16 runs. And then for each one of these legs, we ran 60 samples and collected 30 samples. So we ran for 60, collected every other one for the measurements that we're going to be discussing. So this is the big DOE matrix. And this was ran for every mold machine combination I just talked about. Let me talk about these variables a little bit. So the first variable is pressure input. So the pressure input is the input that the system pressure is trying to maintain. At the beginning of this presentation, I mentioned the nozzle pressure sensor. That is what I'm calling the MPT here, melt pressure transducer. So that is using the true plastic pressure measured at the nozzle to control the input. Alternatively, we hooked up on the hydraulic machine and on the load cell on electric machine to control the machine. So what that means is rather than controlling from plastic pressure perspective, which you get from the nozzle pressure transducer, we want to understand how much do you gain or lose when I'm instead just using my hydraulic pressure or my load cell on my electric machine to control the process. So again, MPTs for that section of parts, and here is based on the hydraulic or load cell, the machine specific control. Next thing on the list was AVA trigger. So this is, if we go back to what AVA is, one is melt travel, the other is cavity pressure. So here is melt travel, right? We use melt travel trigger based on screw travel. And then we also had cavity pressure based targets where the AVA trigger was utilized. Next, the PFA trigger. So this is the shape that the PFA reacts to. As you'll recall, when I talked about PFA, you can either have a virtual one, right? That is where the user is defining the shape, the magnitude, and it's always consistent. It'll give you the same shape every single time. Versus the actual, right? So the actual cavity pressure sensor that's installed in the mold, how does that react to PFA? And then finally, resin condition. So we wanted to test a virgin, so we ran 11 MFI polypropylene in all these molds, just maintain that for the full 60 sample run. And then we also did a variable where we ran 11 melt for the first half of the run, and then switched to a 35 melt halfway through. And we didn't do any purging or anything. That was just going from one to the other and letting it run through. So these are all the experiments we ran. The reason it was set up like this, we wanted to understand how does the nozzle pressure sensor, how important of a role does that play? How important of a role does cavity pressure play in the AVA algorithm? How important does cavity pressure play in the PFA trigger? And then how does that impact both in a virgin resin run or in a run where I'm creating variation in my raw material? Okay, so the first one we ran the baby flip lid, baby care wipe lid. Here is where the gate was there's a cavity sensor. This was at end of fill. Here's the representative process. Just wanted to show you guys a graph what this thing looked like. Here is my pressure set point. Here you can see velocity. So that's that speed out early on as it's slowing. And then here is the end of fill cavity pressure response that it's responding to in PFA. So you can see I had a PFA of negative 0.5 for this experiment that was reacting to that end of fill cavity sensor. High level, by the way, there will be a very in-depth white paper that we'll be releasing, I think today actually, that covers all of this. So if you want to dive into all this raw data, that will all be in that white paper and read to your heart's content. But high level results of the baby care wipe lid is what we did is so for this I had part specs. We weren't using the actual resin, I don't think, but because we had specifications, we were able to look at things like CP, CPK, PP, PPK. So what you're looking at here is the PP as it would have been for each one of these versions. End of the day, what did we find out? We found out that load cell based control, so a machine based control, not nozzle pressure control, with cavity pressure feedback improved 2 of 5 dimensions with virgin resin, none of them being statistically significant. So marginal improvement. However, we found in the virgin or in the variable resin, right, when we forced a change in the resin, all 5 of the dimensions improved when using cavity pressure feedback. One of those being statistically significant. So statistically significant improvement in part variation. Next one, small ASTM. Again, here's the process. Speed up front, slows down. Here's that end of fill sensor that was installed right here on this part. That's reacting in our PFA. So there's my PFA setting. You can see auto viscosity adjust in this specific picture has already drove the process down 25%. The results here. Well, one, we had some problems with some short shots when we ran the variable resin, which I'll mention. But load cell based control, again, machine based control with cavity pressure feedback improved 3 of 4 dimensions in virgin resin. And in variable resin, we ran into these short shots. So where we could draw conclusions that had a lot to do with when we were running the MPT, not the cavity pressure based ones, but the virtual based ones, which kind of confused the data a little bit. But again, we saw a big improvement here of load cell cavity pressure based processes versus MPT based virtual feedback. Then the last one I mentioned is the 4 cavity dose cup, which we ran in a RoboShot. What's different about this part is my gate location and sensor location are extremely close to one another. You think of it as a post-gate sensor. So here you can see there's the process as the pressure comes up. Here you can see the cavity pressure responding immediately after the process starts. So auto viscosity adjusts, my time target on this was 0.33 seconds, right? I have to make a determination almost immediately in the injection profile. In addition, PFA reacts very, very early in the process because I'm realizing that pressure so soon. So what we wanted to include a post-gate sensor here, and as you'll see why, it actually made it worse. So one of the lessons in all this is an end-of-fill sensor is definitely the way to go when for low constant pressure molding, as far as the feedback loop is concerned. So in this instance, load cell-based control improved 2 of 3 dimensions. But in the variable world, it improved 0 out of 5. In fact, it didn't improve any of them. So, end of the day, I think what we're saying is end of fill sensor. So when an end of fill sensor is utilized for PFA response and AVA calculations, we improve 10 of 14 dimensions. So 71% of those dimensions and 2 of those molds were improved with the end of fill sensor. With the post-gate sensor, is utilized for PFA and AVA calculations. The nozzle pressure sensor, the MPT-based control, improved 4 out of 6 dimensions. So I think what we're saying here is, end-of-fill sensor is definitely the way to go. Your post-gate sensor, again, provides a litany of great information, but you probably don't want to use it for doing control loops around PFA and AVA, is what we've learned. So conclusion, again, I recommend you go read the white paper. But utilizing the machine load cell or hydraulic pressure system, coupled with end-of-fill cavity pressure sensors, often improves the influx system performance. So the MPT improves the influx system performance versus that of MPT control with virtual sensor feedback. A better way to say this is at the end of the day, an end-of-fill cavity sensor, right, inside the mold, improves low constant pressure algorithms to the point that control based on nozzle pressure sensor is not necessarily required. Let me try and simplify that even more. What does this mean? Here is the new hierarchy, at least based on this experiment, of constant pressure control. Best way to do this is, both end-of-fill sensor, right, and a nozzle pressure sensor, right? If you can do both, that is still, the gold standard, as we call it, for constant pressure control. However, now as we get into what's the second best one? Well, the second best one is an end-of-fill sensor and not a nozzle pressure sensor. For all of you out there that are using cavity pressure sensors today, there's an opportunity for you to utilize this without necessarily installing nozzle pressure sensors on your machines. If they are absent, cavity pressure sensors in your mold, then you probably do want to go down the nozzle pressure sensor route. What's neat about this though is, being able to utilize constant pressure control. And if you already have tools out there with cavity pressure sensors and all those benefits that they provide, your success will be even better in the cavity pressure based system, again, based on these case studies, than relying on the nozzle pressure sensor alone, which is number 3. So this would be like your base influx system. It's a nozzle pressure sensor, but virtual cavity pressure feedback, which is actually the third best. In my experimentation, having an end-of-fill sensor is better than having a nozzle pressure sensor when running an influx constant pressure based control. And it's, to me, it's not super surprising, right? Like you think about what cavity pressure did for a decoupled molding process. Hopefully it makes sense to see why cavity pressure can also be so impactful to a constant pressure process as well. That's really what I was hoping to get out of, not only this case study, but explain to everyone today, like as RJG's horizons broaden and our core technology, cavity pressure sensors, allow things like autonomous molding to achieve things that may not other be achievable without the use of cavity pressure sensors. And why this, why is RJG going down the autonomous molding route? I think you're starting to understand why, because of how much benefit, their legacy or our typical technology improves these systems specifically. It makes a really good match, constant pressure molding with cavity pressure feedback. Things like PFA, right, that are going to follow the topography of that cavity curve, or auto viscosity adjust that's going to make those adjustments based on cavity pressure feedback. Data shows that that really improves the system quite dramatically and allows our customer bases some flexibility in how they want to approach constant pressure molding for their own applications. That is the presentation, all 46 slides. I know I talked kind of fast there. Um, and then I think we're going to open it up to some questions.
Yes, Brandon, thank you so much for that. So yes, if any of the attendees have a question, please go ahead and send it to the chat. We did get one in there already, and a couple to me directly. If you can control the inject signal, why not just have the system directly trace a reference curve so that you have the same in-cavity process each time? Would that not get rid of the need for AVA?
Yeah, no, good point. Yes, that is a doable thing. In fact, Kyle, you're thinking ahead. That's probably, a path we'll go down one day. What I would say about that though is, although that's true in say a mold that doesn't change, if you were to say lose cavities or maybe have a significant shift in viscosity, you may not want to trace that same velocity curve. If all things are the same, then absolutely, I think that's doable. But you may find a scenario like maybe I have an 8 cavity mold and I need to run 6 cavities. I could block 2 of those cavities, get a different velocity response out of that system because it'll adapt. In that scenario, right, the machine you run the risk of preordained movements. So your statement is factually correct. You could just say, hey, this is my velocity profile. Just keep doing that same thing over and over again. But there is a risk in preordaining what the screw is going to move without, part of the value of constant pressure molding is the mold is telling it what's happening right now at this exact moment in time. So it's able to handle changes that may happen environmentally over a long course of a run. So your head is in the right space. I can see where you're coming from with that, but it doesn't allow us to adapt to really bad scenarios, if that makes sense.
And then just a quick follow-up from Kyle is what was asked being revealed at K Show, i.e. the new system that is being unveiled.
Yeah, so there will not be a system running at K Show, unfortunately. The our RJG buying iMFLUX and getting everything ready for that. Unfortunately, we ran out of time. However, we will have a video of iMFLUX running on a Copilot, constant pressure molding, running on a Copilot, and making parts. And we'll have those parts in that video at K Show to kind of show off our new tech.
Nice. All right. Another question, Brandon. Is the process compatible with glass-filled materials?
Yeah, it definitely is. I would say, I, I get asked all the time, where does low constant pressure molding not do well? One area I will tell you, and I'll just be honest with you, is if you want to make pretty parts, pretty glass filled parts. What I mean by that is let's say you're running a 60% glass filled nylon and you want it to be pretty. Well, the way you make that thing pretty is you make the surface resin rich. The way you make the surface resin rich is a lot of shear, right? A lot of speed. As you saw in the iMFLUX process, it wants to slow as pressure is maintained. So you won't get that resin-rich surface. Aesthetically, that is, you could see that as, a downgrade. However, what it also shows is, one of the things we show, we tout is like improved weld lines. And the idea here is, shear, although it'll make like a glass-filled part look pretty, you're separating all the constituents in that polymer. So when weld lines come together in that scenario, you're getting 2 resin-rich surfaces that are combining with each other because of you wanting to get a certain aesthetic. What you're not going to see in a low constant pressure process is all that shear causing the constituents to separate like that. It's going to be much more homogeneous. So I would say, can we mold glass-filled materials? Absolutely. Can we make them as pretty as you can when you just inject with high speed? Probably not. Some of that glass starts to bloom to the surface near end of fill. But like I said, I think there's some advantages to that, but there's definitely some disadvantages as well.
Definitely. Um, is the old pressure pilot in the back screens of the original iMFLUX controller available slash will be available?
So the influx retrofit business still exists today, down in Cincinnati. So if you wanted to retrofit your machine, you can actually go out and buy, the legacy influx controller, and whatnot. Um, we are working on migrating all of that into the new Copilot. When the new Copilot exists with the low constant pressure molding, modules in it, that will go away. That pressure pilot you're talking about, Kyle. For the existing retrofit systems we are putting out there, you do have access to that. Hopefully that answers your question.
Yeah. And then a lot of the parts that you kind of talked about were maybe on the smaller side. Does this also apply more to like larger scale parts, maybe for the automotive industry or just larger parts in general?
Yeah, actually, it performs probably better. Yeah, so a lot of these examples I showed here were kind of smaller packaging, P&GS parts. But when we get into really large components, so think like large automotive, whether it's door panels or dashes, or even think, large packaging, so trash cans and buckets and things like that. There's a lot of benefits that can be seen here. That's when you start getting really good benefits in the reducing tonnage side of the world, right? You know, if you think about the ROI and what's my return on investment from running a 150 ton versus a 200 ton, there's some savings there, but it's not massive. Well, if I can go from a 1,000 ton to a 600 ton, now there's some pretty big capital savings that can exist. So I get excited in the high tonnage world because we usually get some really good ROI capital savings for reasons like that. There's just bigger spend pools in the higher tonnage world as well.
Nice, nice. And then just the only other question that I had come in, Brandon, was that so you'll have this on display basically at the K show, having it and promoting the technology and everything. When do you think it's going to be, widely available to the public, if you will?
Yeah, our goal is first or second quarter 2026. You'll start seeing the first versions of uh, of low constant pressure on a Copilot. Yeah.
All right.
And
Well,
it's important I mentioned it too, but just wanted to reiterate the Influx legacy retrofit business still exists. So you can actually buy that system through RJG with that old controller. So it's not like you can't go out and get it today. You definitely can.
yeah, good point. Um, all right, well, that's all I have, and I didn't see it have any other questions come in. So, Brandon, thank you for all the information today. Very, very knowledgeable, very good presentation. Audience, I hope you gained a lot from it as well. Attendees, thank you for being here. Just a reminder, we did record this webinar, and we'll be posting it by the end of the week. So keep an eye out for that. Thank you again to Brandon and all of our JG for being a great map partner. And I'll now end the webinar. Thanks, everyone.
Thanks.